So I think I can start now. So welcome to this webinar about TLS, Transport Layer Security. My name is Stefan Brinkmann, and some of you already know me, I think. I'm working at the IMA training team in Bad Pyrmont. Yes. So let's have a look here at what am I talking about today. First of all, I will give you an overview of what is TLS, what does it mean? And then I will give you some demos, some practical live demos, how to use it with PLC Next technology. And at the end, there will be time for your questions and answers. So please save your questions until the end. Let me just give you an explanation of what is TLS. So it stands for Transport Layer Security. And it's a cryptographic protocol designed to provide communication security over a computer network, very general. So secure communication, cryptographic communication. TLS is quite old. So the first version was published in 1999 by the IETF. But the first name was SSL, Secure Socket Layer. So maybe you still hear that. So it means the same, it's just the older name of TLS. It was released by Netscape. The company also published the very first web browser that was available, I think. I'm not sure if they're still on the market. They developed the protocol. The current version now is version 1.3, which was published in 2018. So this is the latest version. And there are some very common protocols that use TLS, like SMTPS for mail, FTPS file transfer, and HTTPS, of course, for secure access to web pages. And there are more protocols, but these are very common protocols that use TLS for that security. So what are the properties of a TLS connection? So first of all, it is secure because we use symmetric key a symmetric key to encrypt the data. So data is encrypted. And what a symmetric key is, I will explain in a second. Then we have authentication. So security authentication by means of asymmetric encryption. And it's reliable because each message that is transmitted includes a message integrity check. So you can really see if the data that has been sent is the same that has been received, or if there's some changes or some manipulation inside. So security, authentication, and reliability, these are the key features of TLS, and this is why we are going to use it. So what is symmetrical encryption? This is also known as pre-shared key. We need a key to exchange before the communication between the two communication partners. It's easy to use in small networks, and this is typical for Wi-Fi networks, for example. So somebody can hand out a ticket with a code or a password to you, and then you can just log in. So the distribution of the key in a local structure is very simple. And this can be used for symmetrical encryption. For example, the AES encryption algorithm uses this. So the idea of this symmetrical encryption algorithm is that both communication partners have a key, and this key is used to decrypt and encrypt the data. So both communications partners use the same key. So you can see here, this is literally a key in this case, and they can use the same key to open and close the lock and secure the communication channel. The difficulty here, of course, is if they are not in the same location, but in different countries or something, to distribute the key in a secure way. So this is the challenge, and this is why it's usually used in small private networks, local networks like Wi-Fi and so on. You see typical networks, Wi-Fi network or VPN and transport mode. On the other hand, we have asymmetrical encryption. So there, in asymmetrical encryption, work with a key pair, a pair of keys that are not independent. They are there's an algorithm that is used to create those keys. So we have a public key that is used for data encryption of the recipient. And only the recipient can decrypt the data with his private key. And the private key is something that you really keep private, that you never share. Only the public key, this is what you share. So only the public key must be exchanged over a public network, and that's no big deal. The public key is public, everybody can have it because it's only used for encryption. And only with the matching private key, you can decrypt the data, but the private key is never shared. So this is used for authentication so that we can really see or that we can identify the communication partner. This is done inside of certificates. So here's an example. Before somebody can send a message, he needs the public key of the recipient. The public key in this case is an open lock. So the sender puts the message in a box in this case and encrypts the data with the public key of the recipient, and then he can ship the message, send the message over an unsecured channel. And only the recipient who has the matching private key is able to open the box so that it is ensured that only the valid recipient can read the message. That's the main idea behind asymmetrical encryption. So for the authentication purpose, we use certificates, which are used for asymmetrical signing and encryption of the messages. So the main standard for this is X.509 by the ITU. They have a public key infrastructure system so that you can issue, distribute, and verify those keys. Here's an example. Of course, it's not a real example, but you can see here. This is a certificate for the phoenixcontact.com website, and the issuer, in this case, Google, certifies that the public key in this certificate is really the public key of Phoenix Contact and not of somebody else. So the certificate prevents the replacement of the public key via a man in the metallurgic. So an attacker who will listen and record the session is not able to replace the public key of Phoenix Contact in this case with his own public key because he does not have the valid certificate. In TLS, as I already mentioned, we use both symmetric and asymmetric key, but why do we do it? Well, a very simple reason. Symmetric cryptography is not so secure, so it cannot be used for authentication. And asymmetric encryption is relatively slow compared to symmetric encryption, so this is not really suitable for data encryption. So we use the best of both worlds, which is called a hybrid encryption. So we combine the convenience of an asymmetric crypto system for the security and the efficiency of a symmetric crypto system for the speed. So what does that mean? So encryption, first step is the sender creates an unencrypted document. So this is the raw data that he wants to send. Then this document is encrypted with a symmetrical session key. And of course, we have to send this symmetrical key over the network to the communication partner. So we cannot do that directly. So this is why we encrypt this session key asymmetrically with the public key of the receiver. And now both the document and the encrypted session key are sent over to the recipient. And then he can decrypt the data. First of all, he decrypts the session with his private key. And then with this session key, he can decrypt the data and get the document. This is how it really works. Okay. So we have to talk about something that is called a cipher suite, which is used in TLS what is a cipher suite? A cipher suite is a set of algorithms that help secure a network connection. So it's more or less a contract between sender and receiver, and they have to negotiate some protocols, some encryption algorithms that they want to use for the communication via TLS. So what is part of a cipher suite? First of all, a key exchange algorithm. So for the symmetric key exchange, and the letters here are some very common protocols in that range. Then we have an authentication algorithm. This is for the asymmetric key exchange. Then there's something called a bulk encryption algorithm. So this is a symmetric key to really encrypt the actual data. And then we have an algorithm for the MAC, for the message authentication code. This has nothing to do with the MAC address, so don't mix it up. This MAC here means message authentication code. So this will check the data integrity. Now, these are the main things that are inside a cipher suite. And this needs to be negotiated between the communication partners. So let's have a look at how a TLS connection is made. So we have a client here and a server, Bob and Alice, and they want to establish a TLS connection. So Bob sends something like a hello, which means it's like a message that says, well, I want to use, I want to do a communication with you. And then he sends a cipher suite and a large random number over to the server here. The server gets this hello message and responds by sending a server random, another random number, and his SSL certificate. Now Bob can verify the certificate if Alice is really Alice and not somebody else. And if that is the case, he will send over a master key, which is created with his public key or with the public key of Alice. And now Alice can also verify if Bob is Bob. And if that is the case, she can decrypt the master key that Bob has sent. So they have now negotiated a master key, and this is then used for the encryption and decryption of the data. So once the communication is established, Bob will try to send data, so he has to encrypt the data. How does that work? Well, we have, first of all, of course, the plain text message. In this case, it's a letter, dear Alice, I hope you are fine. Then he selects the encryption algorithm that they have negotiated in the cipher suite. So in this case, it's AES 256. And for that, he uses the shared session key that they have negotiated. Result of that is the encrypted message. And to check also the data integrity, a second algorithm is used with the same session key and also some parameters like IP address and ports. And this is called the MAC algorithm. The MAC algorithm will create a hash, the so-called message authentication code, which is also sent. So the encrypted message and the MAC are put together in a message, and this is sent over to Alice. And now Alice receives this message, and now she can decrypt the data. So this procedure is also called authenticated encryption with associated data, AEAD. Okay, right. So Alice has received the message. So the encrypted message plus the MAC, the hash. And now, first of all, she untags both so that she has the encrypted data and the MAC, like this. And now she has to check if the data is valid or not. So has to make an integrity check. So what she does is here, she uses the encrypted message, sends it to the MAC algorithm, with the shared session key and the IP address, and she calculates the message authentication code of the received message. Now the MAC of the received message is compared with the hash or the MAC that was shipped with the message. And if they are both the same, Alice knows that the sent message is exactly what she has received, so there has not been a change. And if that is valid, then she can start to decrypt the message. So uses the same algorithm to decrypt the data with a shared session key, and at the end, she will have the plain text message. So basically the reverse of the encryption. Maybe you heard of a different algorithm that is, or a different protocol, which is called IPsec. This is also secure communication. And I just want to point out a little bit of the differences. So IPsec operates on a different network layer, on layer 3, whereas TLS is working on layer 4. So IPsec provides security services such as authentication, confidentiality, and integrity for IP packets. And this is used for end-to-end security between network endpoints. Basically, this is what we are using for VPN. It's just a different topic. It's just on different network layer. So it's used for VPN connections, more or less, or to secure to secure whole networks, and not a communication between two communication partners. And TLS, as I said, working on layer 4. Also encryption, authentication, integrity check. And I mentioned the protocols, so HTTPS, SMTPS, and FTPS, very common. So this is just between client and server, so just on a different layer. Yeah, this is what I said. It's widely used to secure client-server communications over the internet for web browsing, secure email transmission, and so on. So IPsec is for VPN, more or less, and TLS is for secure TCP/IP communication. So let me give you some use cases. The first use case, very simple, using an HTTPS connection to connect to the web-based management of a PLC Next controller. So let's have a look here. So this comes later. So let me just open a web browser. And now I try to open the web-based management of a PLC Next controller. And typically what you see is here, you get this message with the first contact. Your connection is not private. Attackers might be trying to steal your information and so on. You see here it's not secure. HTTPS is not active. And this is just because the certificate that is used for authentication is a self-signed certificate issued by Phoenix Contact. And my web browser by default does not know Phoenix Contact, so he cannot verify if this is a valid certificate or not. So Phoenix Contact is not known. And this is what he's telling me. I cannot really, the certification authority is invalid. I don't know who issued the certificate, and it's not secure. So I can get some information. What I can do, of course, is click here on advanced. And it tells me, yes, so I cannot verify the certificate. You can continue unsafe. Of course, I can click here now and go to the web-based management because I know it's my HPC here that I have. So I trust myself, but you see here, it's not secure, which means it's not encrypted and nothing. So how can we change that? So we need to add the certificate to the web browser's certificate management, and then the web browser and the next time can verify the certificate and enable HTTPS. So to do that, we can go to configuration in the web-based management, go to web services, and there you see there's an HTTPS certificate. So I can click here on regenerate a certificate to create a new certificate. And do not forget to apply the certificate. Very important. Okay, so. And now I have to export the certificate. So this can be done if I go to security, certificate authentication. If I go to my identity tool, here's my HTTPS self-signed certificate, and there's a download button here. So I can save this certificate. In my downloads folder, you see HTTPS self-signed certificate. I click on save. And now I'm using the Edge browser, but this also works for other browsers. So I click here on the 3 dots, go to the settings. And then there's a section called Privacy, Search and Services. If I scroll down here, you can see here there's Manage Certificates. I click on this one here, and then there's something called the Trusted Root Certification Authorities. And this is where I have to import my certificate that I just exported, browse. So I add this certificate, open, just click on next, finish. Now I say, yes, I want to install the certificate. Okay. So I need to close my browser, open it again. And now the browser knows who Phoenix Contact is, or who the Phoenix Contact certificate authority is. And I hope you see it takes the first time it takes a little longer. So the message is gone, and you see HTTPS is enabled here. And if you click on the lock, you see now your connection is secure. This site has a valid certificate issued by a trusted authority. This is one use case of TLS, using the self-signed certificate to log in on a secure way to the web-based management. So, second use case, secure OPC UA. So I have here a program with some sample data, and this is I have enabled here a variable that is just counting up, and I have enabled OPC. So this is transmitted via OPC. This is also working with certificates. So I have to create or I have to export a certificate and install that on my OPC UA client. So where do I find the certificate? I just open the web-based management of my PLC. Let's log in. On security, certificate authentication. If you go to the identity store, here you find your OPC UA self-signed certificate, which you can download. This is the server certificate. And as a client, I'm going to use the UA Expert. And there is a specific folder inside UA Expert. All these examples I put in the documentation that you can download. So it's in app data. It's a hidden folder in Windows. So %app data, %. And they will find a folder called Unified Automation, UA Expert, and then there's the PKI, Private Key Infrastructure. There's a trusted folder, and there's the certificate folder. And this is where I have put in my OPC UA certificate from Phoenix Contact, from my PLC. Once you have installed it, You can just start UA Expert. Make a connection to the server. And then you have a connection. So you see here my counter variable is changing. And now I can make a Wireshark recording. So I will do a live recording here. And you can see here I have a filter OPC UA. And I hope you can see it. It says now UA secure conversation. So you see request response, request response. And it's a secure conversation. So using using TLS as well. The last use case I want to show you is TCP/IP communication between two PLCs with TLS. So in my system, I have an Axelan F2152, which is the server, and I have an HPC, which is the client. And I have created a small program that is used for the communication. So to make this possible, you have to create your own certificate. So I'm not going to show how to create certificates in this session, but you find information on that also in the documentation. And you have to create your certificates yourself. So it would be just take too long to show how to create these certificates, but the process is also in the documentation. So for this, I need, of course, to install the certificates for both sides. First of all, I need to have a certificates in the identity store. And here I created a new section, which is called TLS local. And this is where I put my certificate, the local certificate inside. So TLS local is the name of the store. And then in the trust store of my server, I have a TLS remote. This is where I put in the remote certificate. And on the client, I did the same. So here my certificate authentication identity store. I have also TLS local. Now here's the local certificate of the HPC. And in the trust store, I have created a TLS remote where the remote certificate is installed. This is what you need to do first. And then you can just create your program. And the first thing that you need to do is to specify the name of the identity store and the trust store. And there's this UDT Connect infrastructure that you can use. And this is where you need to put in the names of these stores. And then I use the TLS socket. So these are firmware function blocks. So they are already included. You don't need to install a library or something to use this functionality. So I've activated my socket and I'm here on the 2152, which is the server. So is server is true. And then I specify the local IP address and my port that I want to use for the communication. Then I have here the structure UDT connect info. This is mainly what I said, the place of the certificates. And of course, start TLS is set to true because I want to use TLS communication. If this is set to false, then the certificates are not used. And when that is done, and you can see here, I have a handle here and an active communication, no errors. Then I can use the send function block. You see send secure is set to true. And here my send buffer, I just put in just an array. So this is where I put in my value here. And I can just open the web-based management. Oh, sorry, the EHMI. So you see here, this is the server. And I can also, just a moment, open the client. So the receiving part. side by side. So you see communication is working. Of course, there's a small delay. I'm just updating every 2 seconds, I guess. So there's a small delay, but you can see that the communication is working. Okay. For some reason, the web server cannot reach. So this sometimes happens if you're inside a virtual machine. But you saw that the communication is working. You can see here it's still running. So communication is still there. Yeah. So basically, you create the certificates for both machines, and then you just install the certificates in the trust store and the identity store of both communication partners. Then you just specify the folder here, and then you can, with that set, then you can just use TLS communication and send or exchange data between 2 PLCs really on an IEC 61131 program. Okay. So that was my last use case. And of course, now it's up to you. Do you have questions? Don't be shy, you can ask. Or was it so clear for everybody?
Hello, Stefan. I have a question.
Yes.
Is it possible to use the same certificate for different communications, like HTTPS and OPC UA, or do you need? Okay.
Now you can use the same. So for OPC UA, I needed a different certificate in this case because it's the certificate. Sorry, let me just go back to the web-based manual. So in this case, I used for OPC, it's a different certificate. Actually, you could use the same certificate, I would say, but then you have to replace it. Because here, if you go to the certificate authentication in the identity store, the OPC UA self-signed certificate is already there from Phoenix Contact, but you can replace it with your own certificate if you want to, and then you can use basically the same.
Okay.
But in this case, I just used the already existing one, so this is why I had different one for this here.
But it makes sense to have different certificates if you want to exchange or extend your interfaces, then that's not linked with the same certificate. Yeah.
So what I also did here, I used my own self-signed certificates or the Phoenix self-signed certificates. Of course, you can really buy certificates from a trusted organization and also upload them here. It's just a matter of how secure you want to have, what kind of security level you need. But it's also possible to add more keys here. All right. Anything else? Something in the chat? Do we need a different certificate for each PLC? Yes, you do. And what about OPC UA certificates and different PLCs? What do you mean by that? So each platform has its own certificate.
If I use now OPC communication, OPC UA communication, so I need for every client a different certificate.
Yeah, each client has its own certificate. Yes, so each PLC has its own certificate by default. No, that's unique. Otherwise, it doesn't work. Okay. It also depends. Sometimes in the certificate, you also have to add, sometimes at least, the IP address, which is used on the client. So for identification purposes, also the IP address sometimes is included. So that makes it also obvious that you need a different certificate for each client. Right.
Another question.
Yes. There's something. Yes, I used XCA for the certificate creation. There are different tools available. One of that is XCA, which is open source. I think I have it specified. You can also use OpenSSL. to create certificates, so there are different ways to do it, but I used XCA. If you go to the PLC Next community, there's a chapter in the forum, I guess, or in the makers blog, which gives you detailed instructions on how to create a certificate. If a PLC is broken, we make a complete backup to a new one. Will the certificate still work with a new one? If you want to use the same certificates, then you really have to export. You can export the certificates from the web-based management. Yeah, you have the download button here and store them. And of course, you can add on the new PLC, you can add the certificate if you want to use. But typically, if you replace a PLC, also the certificate will change. But if you don't want to do that, you first have to export the certificate, store it in a secure location, and when you replace the PLC, then you have to go to the certificate identity store here and add the certificate. Now that's possible. But this is a manual process, so there's no automatic process of doing that.
And then you need to keep the IP address the same for certificates which use the IP address to calculate keys.
Yeah. So this really depends. Sometimes there are also some other features. So if you go here to PLC Next on the OPC UA server, just let me go offline. So you can see here, if you go to the security section, you can see a type of subject, and there you can also add IP address. So this really depends. In this case, it was not required, but sometimes this is required depending on the client and the server, or at least on the client. Some clients need to have the IP address here of the server and vice versa. So this can be included here, but it really depends. Yeah, but that's the point. So if a PLC is broken, the new one will have the same IP and certificates. Yeah, so the certificates will not be the same, but the IP address, yes, of course. If you want to use the same certificate, then you have to first export it, store it somewhere, and manually install it. Then you can use the same certificate, and then it should also work. Be also aware that the certificates have a expiry date. So this certificate here is valid until 2029, and then you have to create a new certificate. So they are not valid for a whole life, at least not all the certificates. Some certificates you can see here, some are valid until 9,999, so forever, but some certificates have an expiration date. Also the ones that I use for the TLS communication, they just expire in 2029. Now this is very typical, so you have to renew the certificates. But of course, it's up to you. If you create your own certificates, you can also adjust the expiration date and make it also forever if you want to. But this is not so secure, so it's more secure to change the certificates once in a while. Okay, anything else? Did I miss something? How to handle the certificate updates? Yeah, just going to the web-based management, to the store and install this. This is, at the moment, as far as I know, this can only be manually done via the web-based management. There's no automatic way to do it, I think. Okay, so if there are no more questions, I would like to thank you for your attention, your participation.